Now let us go back to our main goal, which is solving systems of linear equations. If we have a given linear system, first is we write the augmented matrix of our system from what we learned in part 1. Step 2 is to write that augmented matrix in its reduced row echelon form from what we learned in part 2. The third step is to write the resulting matrix, the one in REF, and to write it back to linear systems, the one with variables now. And our last step, if we have now our linear system, then let us solve it like how we usually solve it before. We use back substitution. This method is called the Gauss-Jordan elimination method. Let us try one example. Let us solve this system. Our first step is write this as a matrix, as an augmented matrix. We already saw this system actually from part 1. There we wrote the augmented matrix of this linear system as this. Remember, the left part are the coefficients of the left-hand side of each equation in our system, and the right part of the augmented matrix are the numbers on the right-hand side of our system. Now, this augmented matrix is actually the given matrix from the exercise in part 2. So if you answered our part 2 exercise, you will get this matrix. This is the REF of our augmented matrix. And we write this matrix back to a linear system. We get this one. Right, so 1 times x sub 1. Then we have 0, 0. So we have here 0x2 plus 0x3. For our second equation, we have 0, 1, 0. And that reflects here in our coefficient 0, 1, 0. The negative 2 on the right side. And lastly, 0, 0, 1, 3. So we have here 0, 0, 1, 3. Okay. And if we eliminate the zeros, we get x1 is equal to 1, x2 is negative 2, and x3 is equal to negative 3. And that is our final answer. Now, it's not always the case where the solutions exist and the solutions are unique. We will see it here in our next example. Let us solve this system. We can in fact solve this using the usual elimination method, but just to illustrate our new method of solving, and that we don't always get solutions, let us use the Gauss-Jordan elimination method. The first step is write its augmented matrix. So we have 2, 10, negative 6, and negative 1, negative 5, 4. Next, let us transform this into a matrix in REF. So what we can do here is we can divide first our row 1 by 2, because we want our leading one in our first row. So 2 divided by 2, that would be 1. 10 divided by 2, that is 5. And negative 6 divided by 2, that is 3. Now we have our leading one in the first row. Let us make the entry below the leading one a 0 by adding row 1 to row 2. Right? If we add this 2, we will get here 0. So negative 1 plus 1, this would be 0. Negative 5 plus 5, this would be 0. And 4 plus negative 3, we have here positive 1. Indeed, we have 0, 0, 1. So after that step, we fortunately got the leading one as well for the second row. Here, this is our leading one for the second row. So all we have to do now is to make the entry above our second leading one is 0. Let us make negative 3 0. To do this, add 3 times the row 2 to our row 1. So multiply 3 to our row 2 and then add it to our row 1. So if we multiply 3 to our row 2, we have 0, 0, 3. Add it to our row 1, we have 1, 5, 0. Finally, we got the REF of our augmented matrix. This is in REF, right? Because you have now the leading ones. They are in order. The leading one is to the left of the next leading one. And for all columns containing the leading ones, all other entries are 0. So this is in REF. And if we write this back to linear systems, back to x and y, we have x plus 5y is equal to 0 for our first row. And the second row gives us 0x plus 0y is equal to 1. The second equation gives us 0 is equal to 1, which is never true. Therefore, no matter what x and y values are, this system is never true, hence, no solution. Lastly, let us consider this system of equations. X minus 3z is equal to 5, and x plus y minus z is equal to 12. So 2 equations with 3 variables. First step, the augmented matrix. It is this one. 1, 0, 0 because there is no y here in our first equation. 1, 0, negative 3, 5, and 1, 1, negative 1, 12. Then let's write this in REF. The row 1 already has a leading 1, so let's just make the entry below it a 0. What we can do is add negative row 1 to row 2. Or we can add negative row 1 to row 2, or row 2 minus row 1. So 1 minus 1, that is 0. 1 minus 0, we have 1. Negative 1 minus negative 3, that is negative 1 plus 3, that is 2. And finally, 12 minus 5, we have 7. There you have it, 0, 1, 2, and 7. Then that's it. The leading ones are in order already. And the entries on the column of leading ones are zeros. So this matrix is already in REF. Let's write this back as a linear system, one with variables x, y, z. We have here x, 0y, negative 3z. And for our second equation, 0x plus y plus 2z is equal to 7. If we isolate x in the first equation here, we get x is equal to 5 plus 3z. Likewise for y, we get y is equal to 7 minus 2z. Why do we have here z to be any number? Well, there are no more equations that restrict z, so z can be any number. Therefore, our solution to this system is that one already. 5 plus 3z for x, 7 minus 2z for y, and z can be any number. So for example, if we choose z to be equal to 0, then if z is 0, x is 5, and y is 7. Oops, this is wrong. This should be 5, and y should be 7. Interchange this. Instead of 7, 5, we should have 5, 7, 0. And if we choose z is equal to 1, if z is equal to 1, 5 plus 3, x is equal to 8. Okay, interchange this again. X is equal to 8. And if z is equal to 1 here for y, we have 7 minus 2, 5. So this is 851. So 571 and 851 are example of solutions for our system. And this system has infinitely many solutions. As an exercise, solve the following systems of linear equations using the Gauss-Jordan elimination method.